Good morning all. Today we shall learn how to find the moment of inertia of an annular ring about an axis passing through its center and perpendicular to its plane, and also about its diameter. So before we start, we have to see what an annular ring is. It is just a thick ring of inner radius, R1, and outer radius R2. So we have to assume certain things. So let's assume that M1 is the mass, M is the mass of the annular ring. As said above, R1 is the inner radii and R2 is the outer radii. So our aim is to find the moment of inertia about an axis, which passes through the center. Let's put it as AB axis. And it shall also be perpendicular to this plane. So before we start, we have to know certain things. We have to know that the moment of inertia of a ring about an axis passing through the center and perpendicular to its plane is, what is it? It is mass into radius square. So with this knowledge, we have to start our derivation. Let's put this as equal to 1. Now we have to find the mass per unit area of the annular ring. That is mass divided by area. And we have assumed that mass of the annular ring is M. And area will be pi r square. Since we have inner radius and outer radius, it is pi into R2 square minus R1 square. So this will put it as equal to sigma. Let's give it an equation number 2. So just think about it. Now coming to the derivation, as we have calculated the mass per unit area, now we have to calculate the moment of inertia. So we can see that a concentric annular ring is made up of different concentric circles. So I can also imagine another circle. See? So you have another circle like this. So you can imagine different types of circles to be made up of. So here I put in as, I consider a green circle which is at a distance small r away from the center and has a thickness dx. Now tell me, what is the face area of the green ring? It is 2 pi r into the thickness dx. This we put it as equation number 3. Now we can say that we can find the mass of the green ring. What is the mass of the green ring? Mass per unit area into this face area of the green ring. So that is equal to, just tell me. So mass is sigma, mass per unit area into the face area. That is nothing but 2 pi r dx. And we know moment of inertia of the green ring can be found by using the equation 1, which we have told that it is equal to mass into radius square. So mass we have found out here as 2 pi r sigma dx times, what is it? The radius square. And here the radius is, tell me, it is r square. So we can find the total moment of inertia. We'll put it as I of the whole of the annular ring. What we have to do? We have to integrate from, tell me, from R1 to R2. And we have, so here R is here, R square is here, and this R will become R cube sigma dx. And we know that 2 pi sigma are all constants. So I can put this equation as equal. 2 pi sigma times R1 to R2 into integral r cube dx. And we know that integral r cube dx is nothing but equal to r raised to 4 by 4 in the limits, tell me, r1 to r2. So this can be written as 2 pi sigma r2 raised to 4 by 4 minus r1 raised to 4 by 4. Okay, now we can substitute for the sigma, and we know that it is equal to 2 pi, what is sigma? Mass. Okay, I'll just put it in another so that you can easily get to it. Sigma is m divided by pi into r2 square minus r1 square, and this, you can imagine, it is, you can take this 4 outside, divide by 4 into r2 raised to 4 minus r1 raised to 4. So we can cancel off 2 and 4, pi and pi, here you get 2. So the remaining thing is equal to m divided by 2 into r2 square minus r1 square, and this can be written in the form a square minus b square is equal to the a plus b into a minus b. So I can put it as equal to r2 square plus r1 square into r2 square minus r1 square. So I can just cancel off this and this, and finally I have the moment of inertia as equal to m divided by 2 r2 square plus r1 square. So we have got a beautiful equation for the annular ring. Now we can just take the cases. Case 1 for a ring. So for a ring you don't have the inner radius and outer radius, very small thickness. So you can just put it as r1 is equal to r2. So from this equation, probably it is third one. So I is equal to m by 2 into, so we just put it as r2 square plus r2 square, which is equal to m by 2 into 2r2 square, or it is equal to, you can cancel off mr square. Okay, that we have to write. Again, you can use this to get the case for a disk. Case 2 for a disk, I is equal to m by 2. So here in a disk you have r1, you don't have r1, you have just the outside radius, so r1 is equal to 0. So m by 2 into r2 square, this plus 0. So it is m by 2 m r square by 2. So we can get the two things out of this annular ring case. Now we have to speak about, or we can derive the next one, that is moment of inertia of an annular ring about a diameter. So just imagine a ring, okay. So I just don't want the fills, so just leave it. Okay. then I have to make it an annular ring, right? So have another ring. Okay. So this has to be rubbed off. So I'll put it inside. Okay. Now I have to find out the moment of inertia about a diameter. Okay. About a diameter. Sorry, this has to be, again, I have to rub that off. About the diameter y prime. So I know the moment of inertia about an axis passing through the center and perpendicular to its plane as equal to m, just tell me, m into r square, r2 square plus r1 square by 2. Okay. Now I can very well use a perpendicular axis theorem, which says that this, I'll put it as x prime x. Okay. Then I'll say that if I put this as Iz, okay, so here I put Iz as equal to, and this as Ix and this as Iy, then I have from perpendicular axis theorem Iz is equal to Ix plus Iy. Since it's a circle, it has the same moment of inertia, Ix and Iy will be the same, so it will be 2Ix, and Iz is nothing but, here I have substituted as m by 2 into r2 square plus r1 square. Okay, so now this 2 will be taken down, so it will be m by 4 r2 square plus r1 square, moment of inertia. So we know that Ix is equal to Iy. So we have the momentum of inertia about a diameter for an annular ring is nothing but m by 4 into r2 square plus r1 square. Hope you could understand, and thank you for listening. Now you can also calculate cases for this about a diameter for a ring and a disc. Do that as an assignment. Thank you all.